Now we will see the force between two parallel currents. Before that, what is the force on a current carrying conductor when it is placed in some external magnetic field? So let's say that you are going to place one current carrying conductor, so which is going to carry some current. So again, let's say this is the external field that you can show over here by B. Then again, the velocity of charge. So we know that current is nothing but the rate of flow of charge. So the charge is flowing through it with a certain velocity V, and because of which it is going to experience some force, and that direction of force again I have shown over here by this direction, let's say, which is along the Z axis. Now we have to find the expression for that. So the one which is given, I is equals to L bar cross B bar. There is one more expression for that, so which you can write it down, that F is equals to Q into V bar cross B bar. So obviously that Q is nothing but the charge, V is the velocity with which it is flowing, B is the external magnetic field, and since this is a cross product of V and B, your force is also perpendicular to the plane which consists of your V and B. So that's why you can show over here. So you can see this is V and B. Say just assume that it is in the XY plane and this force is acting along the Z axis. So now you have to just derive that another expression also. For that, what I will do, I will just consider a small part of that conductor. Let's say this is nothing but the part DL, and through which a charge is flowing. Then for this part DL, the amount of charge which is flowing is nothing but the dq only, and the force experienced by that small part only, dq, you have to calculate, and finally you have to add all those forces, those small forces, which will finally gets the result for your total force. So let's say now this is nothing but the df bar, so which is nothing but the dq. Again, instead of v, we can write it down it as a dl upon dt. So that is your dl upon dt. Your dl is also vector cross, that is a b bar. Again, I can just do some your arrangement over here by just taking that dl outside, and this is nothing but now dq upon dt cross b bar. So this is your df bar. Again, this one you can write it down, that is a dl, then dq by dt is your I, and this is b. So definitely you can say that now it becomes that dl I cross b, and again further I can just write it down. Definitely this I is a constant, and then you can write it down as a I into L bar cross B bar. So this is actually for your force on a current carrying wire, where it consists of your only one wire, and the expression for that, either you can use this F is equals to Q into V bar across B bar, or you can go for that is I into L bar across B bar. Again, there are few cases. For example, if I consider F is equals to Q into V bar across B bar, which I can write it down, that is nothing but QVB sine theta. Again, if I say that theta is equals to 0, the angle between that V and B, if it is 0, then the force is also 0. Again, if I consider that theta is equals to 90 degree, then definitely that force is also maximum, which you can consider that it is nothing but QVB. So this is the value of your maximum force which will act on that your current carrying conductor when velocity and magnetic field, they are perpendicular to each other. Now again, to find that force between two parallel conductors or that currents, so mainly we are just going to use that Fleming's left hand rule. Yeah, so according to this one, you have to just hold your hand in this manner. So this first finger indicates the direction of your magnetic field, then this one indicates the direction for your, again that is your current, and the thumb indicates the direction of your force experienced by that conductor. The same thing which I have shown over here. The first finger, that is a magnetic field, then this one, that is the direction of current, and you can say that this thumb is going to show the direction for your force experienced by that conductor. So that is a very important rule to just determine the force experienced by that conductor, according to which we can solve the numericals also. So now we will see the force between two parallel currents, that is a current carrying conductor, so which I have shown over here. So let's consider these two current carrying conductors and through which the current is flowing. So you can show like this one. Let's say this is your I1, then this is nothing but I2. We can call it as nothing but your like current because both of them are flowing in the same direction. So if I consider the conductor 1, obviously which is going to produce the magnetic field around it. So you can say that. So likewise it is going to produce the magnetic field around it. Then according to the direction of your magnetic field, so that means you can find it by that your thumb rule. So for this case, so if we just move around that I1, so it is going to produce the magnetic field which is nothing but in the inward side. So let's say at a distance r, it is going to produce the magnetic field which is in the downward direction. So obviously this B1 will act as a source of magnetic field for the current carrying I2. Then definitely again I can say that this I2 will experience some force because it is placed in some external magnetic field and it will experience some force. So this F2 now we have to write it down. So obviously that is a I2 L B1. Again B1 is nothing but you can say that which is your mu 0 I1 upon 2 pi r. That is the field due to your infinite current carrying conductor. So simply you have to put this value I2 L, then this one mu 0 I1 upon 2 pi r. So which then I can say that mu 0 I1 I2 L upon 2 pi r. So this is the expression for this, the force experienced by this conductor 2, and according to your Fleming's left hand rule, you can just check it out the direction. The force is moving on the left side. So this is the direction for your force F2. Similarly now you can do the procedure for conductor 1 by just saying that the conductor 2 is going to produce the magnetic field at every point on this conductor 1. Again you can say that the direction is upward according to that thumb rule. So this is nothing but B2. Now again the same you have to just check it out, the direction for force F1 which is on the right side. Now the same thing you can see in this diagram also, the current which are flowing in the same direction. So the forces which are acting F1 and F2. So definitely this is a force of attraction if it is a like current, and you can say that if the currents are unlike current, they are going to repel each other. So this is the analysis for force between two parallel currents. So they are going to attract if the current is going to flow in the same direction, and they are going to repel if the current is going to just moving in the opposite direction. So that is the thing for your force between two parallel currents.